An acid is a compound formed when, actually it is a compound which when dissolved in water produces hydrogen as the only positively charged ion. So if you dissolve something in water, at the end of the day, you must be in position to produce hydrogen as the only positively charged ion. If something has sodium in it, calcium, and all the rest, you will produce sodium ions. That won't be an acid. That will be another substance, which we know as a base. Bases are of two types. There is base and the alkalis. We're also going to look at them down there. In the first session, we are just going to revise this, acids and bases. Then in the next session, we shall look at basically salts, where we shall calculate something we are sharing on the screen. So here, if you produce hydrogen as the only possible charged ion, an example is sulfuric acid, hydrochloric acid. When they dissolve in water, they produce hydrogen ions and the other ions, which is a sulfate ion or a chloride ion. So examples are these. There are basically two types of acids. We have mineral and organic. Mineral acids, these are called mineral acid because they are derived from minerals themselves. Example is common lab acids like sulfuric acid, hydrochloric acid, nitric acid, and phosphoric acid. Then organic acids, these are derived from organic compounds. When you look at organic chemistry, that's part of chemistry called organic. There is that part where you reach on and say these are organic compounds. Example, these are acids derived from organic compounds. Examples include ethanoic acid. Okay, this is ethanoic acid. One of these. So that is an example. The way you write ethanoic acid, it's not triple zeros. There are 2 zeros. So here we have, they are found in vines, citric acids. Citric acid, this is basically in fruits like the raw mangoes we eat, we find them there, and the lactic acid found in milk. All these are organic acids. But if you take most of them, like citric acid, they have low, since they are organic in nature, the body needs them, though they are acids. But if you take these mineral acids here, you will get in complications in the stomach. All these are dangerous acids. But in biology, they tell us there is hydrochloric acid in the stomach. There is hydrochloric acid in the stomach. That acid is good. It is basically for digesting stomach, actually digesting foods that go to the stomach. That is the use of that acid. In the stomach, it is not so harmful like the way it is, or the way people hear. But if you just take it naturally, this one that is made, that means your stomach will get problems. So basic properties of these acids, if you taste or if you eat a mango, you get that sharp sour taste. That is the property of the acid. That is citric acid in it. All acids taste like that. Even these other ones, they taste like that. So acids change colors of indicators. Like an example, it turns a blue litmus paper red. So here we have this. Acids ionize in water to produce hydrogen ions. So like this one, sulfuric acid, aqueous, it ionizes in water to give 2 hydrogen ions. I told you, if you don't know how to write these ionic equations, they are going to disturb you. We looked at these ionic equations earlier on. So here, sulfuric acid, aqueous. I told you aqueous substances are the ones that ionize in water. They ionize to give 2 hydrogen ions because of these 2. The plus is because hydrogen has a positive 1. This 2 is a valence of a sulfate here. That's why you say a sulfate ion has a 2 negative up. Then hydrochloric acid is hydrogen and chloride ion. This one is one hydrogen, one chloride. That's the way it ionizes in water. Also, most acids are corrosive. They cause burning effects and they are poisonous, especially mineral ones. These sulfuric, hydrochloric, all of them, they burn the body. So here we have dilute acids react with the reactive metals to produce hydrogen gas and a salt. So if you react an acid with a metal, you get a salt and hydrogen gas. So we are going to look at the way you form these salts later on the second session. So don't be worried about that. But when you react an acid and a metal, you form a salt and hydrogen gas liberated. So whichever acid you get and you add a metal, it will give you a salt and hydrogen gas. An example is magnesium plus sulfuric acid, you get magnesium sulfate and hydrogen gas. Sodium plus sulfuric acid, you get sodium sulfate and hydrogen gas. Those are some of the reactions there. Acids react with carbonates and hydrogen carbonates to liberate carbon dioxide gas. This is an example of that. Let me remove these salts of ours. I'm going to look at them later. So here we have the acids. So acids react with carbonates and hydrogen carbonates to liberate carbon dioxide gas. When the acid reacts with a carbonate, a salt, water, and carbon dioxide gas are the end products. Acid and a carbonate, any acid, an example is hydrochloric acid, plus any carbonate. We have those carbonates as sodium carbonate, any carbonate of a metal, you know. So if you look at those carbonates, most of them produce those salts. So if you react it with sodium carbonate here, you get sodium chloride, water, and carbon dioxide gas. Those are the end products. A salt is this, sodium chloride. Water, which is this, and then carbon dioxide gas. Any carbonate plus the acid, even a copper carbonate with the acid, the end product is a salt of copper, water, and carbon dioxide gas. Acids react with bases. Acids react with bases. We shall look at bases down. We shall look at bases down as we discuss. So here, we have these acids react with bases to form salt and water also. Acid and a base react to form salt and water. An example of a base is sodium hydroxide. You get react it with hydrochloric acid. All this must be in aqueous states because solids don't react. Solids do not react apart from a few. So here, sodium chloride is a salt form because sodium is more reactive than hydrogen, takes away what chlorine has, you get sodium chloride and then water at the end of the day. Sulfuric acid is the copper, also behaves the same way. So properties, these are preparation of acids, most of them. We talked about acid anhydrides. Acid anhydride, these are oxides of non-metals that when dissolved in water gives acidic solutions at the end of the reaction. Acid anhydride, all of them oxides of a metal. Oxides of a metal are like sulfur dioxide, phosphorus pentaoxide. This is penta because of this 5. 5 is penta, Fv. So even nitrogen dioxide is NO2. If it dissolves in water, it gives us nitric acid, which is an example of oxide of a metal, and acid anhydride. The end product is water. So by this is the way you prepare the acids. This is phosphorus pentaoxide in water, you get phosphoric acid. This is phosphoric acid, P4. This is 4H3, PO4. This 3 is down, then this 4 is also down here, the oxygen. My camera is disturbing a little, but I want to know if we are moving together. Andrew? Treasure? Treasure?
Yes.
We are together. Ready?
Yes.
Ready?
Yes,
Ready?
teacher.
Are we
Yes,
together?
teacher. Yes.
Okay. Let me hope acids are now moving on.
Yes.
Okay. Here we have another way of preparing acids is by displacing a weaker acid or molar volatile acid from its salt by a stronger acid. Let's look at this. Now, this is not displacing what? This is sodium chloride, is a salt. If you displace, if you react a salt, sodium chloride and sulfuric acid, you will form sodium sulfate, and then this hydrogen will take the chlorine to form hydrogen, this hydrochloric acid, which is aqueous. So here, displacing a weaker acid, this one we are going to look at this type of acid. This one is a mono, this one is a di. We have monobasic, and then we have the dibasic, and then tribasic. You are going to find out that this one is more stronger than this. Though these tribasic acids here, we have tribasic, weak salts. They are weak acids. They are weak. Most of those acids are weak, tribasic. Most of them are weak. An example is phosphoric acid is a weak acid because it is formed as a result of reacting acid anhydride, reactions of those acid anhydrides, oxides of nonmetals with water. So this is what we form. Okay, so here we can also form this by precipitating an insoluble sulfide. Sulfide is S2 minus. That is a sulfide. Sulfide. Now, if precipitating means you get a precipitate is like, I told you last time, it looks like this posho. If you get posho and put in water, you form those posho crystals or posho particles in water. So if you leave it to stay for some time, whatever goes down, what goes down is the precipitate. What comes up is the water. So if you want to precipitate, by precipitating an insoluble sulfide from a metal salt by hydrogen, by precipitating an insoluble sulfide from a metallic salt. Let's take an example, metallic salt of this weak organic compound, which is lead ethanoate. You add it to hydrogen sulfide gas, you will form lead sulfide. Real lead sulfide. This is lead ethanoate. Lead ethanoate, COO. Then there is a ethanoate. If you look at this part here, it is an organic acid derived from organic compounds. That's what you have. These are acids derived from organic compounds. An example is this ethanoic acid. If you remove the H here and replace it with a metal, it becomes sodium ethanoate. Now, if you look at this here, if you look at this reaction down, by precipitating an insoluble sulfide from a metallic salt. This metallic salt is here. This is now lead. They have removed the hydrogen, and the 2 is because of the lead. So it has become lead ethanoate plus hydrogen sulfide gas. You get lead sulfide, not lead sulfate. Lead sulfide. And then ethanoic acid at the end of the day. This one takes the hydrogen, and then the lead takes the sulfide. That's what you form. So here you are forming a weak acid, which is ethanoic acid plus this salt. That's what they are saying here. Now we talk of basicity of an acid. Basicity, take note of that, because in calculations that involve mole concept, they will ask a question, maybe to calculate the basicity of an acid. If they say basicity, don't be scared about the word basicity. This is the number of hydrogen ions that can be produced when 1 mole of the acid ionizes in water. You will look at that later, but here is examples of them. Here we have monobasic acid. Is the acid that ionizes to produce hydrogen ions. They produce only 1 hydrogen ions. There we are meaning it's a monobasic acid. Dibasic produces 2 hydrogen ions. Tribasic produce 3 hydrogen ions. They ionize in water. Ionizing means they separate into ions, or they dissociate. That is a common word they use. Dissociate, ionize in water to give 3 hydrogen ions and a phosphate ion. This is a phosphate ion. All these are in water. When you are writing ionic equations, you find that if you are writing this phosphoric acid, you will find out that it's hydrogen ions and phosphate ions. I gave you all these ions when we were looking at when we were forming equations. All these ions I gave them to you. So make sure you know how to write these ions. So if they say tribasic acids, these are acids that ionize to produce 3 hydrogen ions. If they say dibasic, they ionize in water to produce 2 hydrogen ions from 1 molecule. Then when they say mono, they produce 1. Nitric acid is an example. Mono, hydrochloric acid, and then ethanoic acid. All these are mineral acid. This one is organic. Then here we have sulfuric acid and carbonic acid. They produce 2 hydrogen ions, and then a sulfate and a carbonate because of this. So you don't need to throw away this carbonate because it is part of the ionic equation. Tribasic also, they do the same thing. So here we have a phosphate ion, which is that. So here we have strength of the acid. Strength of the acid refers to the ease with which an acid ionizes to produce hydrogen ions. If the acid separates into individual ions easily to produce hydrogen ions, then that is the strength of that acid. According to the strength of the acid, it can be categorized as strong or weak. There are only 2. Acids can either be strong or weak. Strong acids is the one that dissociates or ionizes completely into ions when dissolved in water. If you want to know that something has dissociated or separated into ions completely, it is shown by this arrow, 1 arrow. But if something is weak, it has a possibility of going back. You show using 2 arrows that if this thing combines with this, it goes back to this easily. That shows that it's weak. So a weak acid is an acid that does not completely ionize in water. Some of the acid molecules do not ionize. That is what we mean by weak acids. So here we have 2 things. We have 1 arrow, we have double arrows. Those double arrows, these ones have mistakes. They have mistakes in them, but those arrows are written as this. This one is okay, then this one down. So those double arrows are like this. You first write like carbonic acid, aqueous, we shall form 1. This one is, it shows that this one is weak. So this one shows that it's weak. If you want to know that it's weak, it gives you 2 hydrogen ions, aqueous, plus a carbonate, which is also aqueous. That is what we mean by weak. So if something ionizes fully, you show it with only one arrow. So you must know that these acids here, like hydrochloric acid, mineral acid, most mineral acids, ionize fully in water. That is how they are strong. Then weak acids ionize partially in water. So some of the acidic whatever remains, and then it ionizes in water. An example, this is ethanoic acid. It gives hydrogen ions. Then the whole of this is an ion, which is ethanoate, which is that. So don't be scared when you find the reagents in the lab written as ethanoates. This is a symbol of ethanoate, CH3COO. So if you want to know that this sodium ethanoate, they put sodium at the end of this. They remove the negative and put sodium. That is sodium ethanoate. So if they remove this and they combine this and put 2 and put lead, this is lead ethanoate. Because lead has a valence 2, it is taken by the ethanoate. Ethanoate has 1. So uses of the acids here, they are found in the car batteries. Those ones, the batteries there, you find the acids, most especially sulfuric. That's what they put there. Sulfuric acid is used in the manufacture of soap, detergents, and paints. That is they use, but they don't use the conch one. They use the dilute. So ethanoic acid is used in preservation of fruits. These ones, normally you find them in home management lab. They are mostly used there. Ethanoic acid, they are preservatives. Even in most cakes, they use ethanoic acid. It is a weak acid. They don't need to worry about eating those cakes. So here, here we have acids are used in the manufacture of fertilizers. Most of them, like ammonium sulfate. If you add ammonia to sulfuric acid, you get ammonium sulfate, which is a fertilizer. Ascorbic acid, this is vitamin C in the body. So nitric acid is used in the manufacture of explosives. Those bombs there, they use these acids. That's why when they use it on you, if you are caught by that bomb, the face will turn into a rough cast. Then let's look at this. Now, before I shift to bases, any questions so far? Unmute, and we talk. Cynthia. Shelly. Anua. Anua. Any question?
No.
No question.
Yes.
Okay.
Actually, has a question.
Who? Patricia. Patricia, you have a question? Yes? You have a question? Okay. If there is no question, yes? We are going to look at this. A base. We are going to look at bases and alkalis. All these fall under the same table or under the same category. A base is a substance which reacts with an acid to form salt and water. Only an acid produces hydrogen ions. A base reacts with an acid to form a salt and water only. So these are bases. Bases are mostly oxides of metals like copper 2 oxide. Copper 2 oxide is written as this. That is a base. Copper 2 oxide. Then we also have zinc oxide. All these are bases, the ones you see here. Then I want to show you a difference between a base and an alkali. Alkali is a base that dissolves in water to produce hydroxide ions as the only negatively charged ion. Those are alkalis. So know the difference between a base and the alkali. A base is a substance which reacts with an acid to form a salt and water only. But an alkali is a base that dissolves in water to produce hydroxide ions as the only negatively charged ion. So alkalis are different from acids. Acids produce hydrogen as the only positively charged ion. Alkalis produce hydroxide as the only negatively charged ion in solution. So let's look at an example here of sodium hydroxide. This is aqueous. When it goes into water, it becomes aqueous. It produces sodium ions and hydroxide ions. This is aqueous. So this one qualifies to be called a base because it has an alkali. An alkali. It produces hydroxide as the only. It produces hydroxide as the only negatively charged ion. So if you look at these examples here, we have sodium hydroxide, potassium hydroxide, calcium hydroxide, all these, ammonium hydroxide, aqueous ammonia. This is what we use. So you find most of these reagents being used in some whatever called the quantitative analysis. They use alkalis mostly. They use sodium hydroxide, they use ammonium hydroxide, and those are the two that help us detect the metals present in an ion. So these two here, they dissolve in water to give us hydroxides as the only negatively charged ion. Here, that is our alkali. Hydroxide as the only negatively charged ion. So after this, you look at properties, general properties of these alkalis. They have bitter tastes. They are soapy. When you touch them, they are soapy and slippery. They turn red litmus paper blue, whereas acids turn blue to red. These ones turn red litmus paper blue. So if you get a solution, if you know that it is either acidic or basic or alkali, you do two tests. You get two litmus papers, blue and red, insert both of them in the same solution. Any effect it makes gives you to know that this is an acid. Yes, this is an acid. So if it turns blue to red, it is an acid. If it turns red to blue, that is an alkali. Alkalis react with acids to produce salt and water. So alkalis, acid plus alkali, you produce salt and water. So sodium hydroxide is an example of an alkali. If it reacts with the acid, so here we form this. If you say alkalis react with ammonium salts to produce ammonia gas, that is what we have. Ammonium chloride is an example of ammonium salt. It reacts with an alkali, which is sodium hydroxide. It reacts with ammonium chloride is ammonium salt. Alkalis are here, sodium hydroxide. You get sodium chloride, which is a salt, water, and ammonia gas. This is a difference between ammonia gas is here and ammonium ion. So there's a difference between this and this. If you want ammonia gas, it is here. It is NH3. This is ammonia. But ammonium is NH4. It has all +1, which is ammonium ion. So if they say ammonium chloride, you must know a chloride is 1. So if they react, they give you ammonium chloride. That is what is there. So at the end of the day, we shall form this. Alkalis precipitate insoluble metal hydroxides from solutions of their salts. This is what they are meaning here. Alkalis, when you react an alkali with any solution of lead, let's an example of lead nitrate. Lead nitrate is also soluble. All nitrates is soluble in water. We shall look at them when we reach that part of salts. We are going to show you how salts dissolve, and you will come to know that when you add this dropwise, when they tell to add dropwise until when the two react, you get lead hydroxide, which is a solid. This one is insoluble, and then sodium nitrate. So if you are asked to write the ionic equation, you must be in position to derive the ionic equation of this. So here we shall have the ionic equation of this as 2 sodium ions, then 2 hydroxide ions. Now I'm going to separate them individually. I don't want these two to remain behind. So here, this is aqueous. We shall form lead nitrate. Lead 2 ions, and then nitrate ions. Since there are 2, we put that 2 here, and then the 3 inside. We form, this is aqueous. We shall form, so we shall form sodium nitrate, which is 2 sodium ions, and then 2 nitrate ions. This is part of this.